Hey everyone, we're looking at our first video, first section, first subsection. So, big storyline for section 1 is functions in general. For this first video, we're looking at subsection 1, so we're looking at functions defined in one particular way, defined from a table. So, our learning objectives associated with this particular subsection are identifying whether or not a relationship between two variables defines a function. We have this little asterisk is telling us that this is an essential objective, so an extra important objective. We're going to interpret the input and output of a function within an applied context. And then we're going to find the domain and image of a function, defined by either a table or a graph. Again, we're going to focus on the table part right here. The little CO thing, these are course objectives. If you look at the syllabus, you'll notice these are kind of our big time overarching themes, and these objectives tie back to those themes. So our big definition that we're going to work from for most of the term, in fact, Math 111, college algebra is kind of a story of functions in general, is this big thing. So what is a function? So at its base level, it's a few things put together. We have some set of inputs, a set of outputs, and then some kind of rule that puts these things together. We often write them as pairs, so you may have seen ordered pairs, especially with graphs in the past. And you may have seen them as X and Y. I've kind of purposefully changed up the letters here because I know a lot of times folks come into college algebra and they've seen some of this content before, either in a high school class or community college or wherever. And X's and Y's are kind of the go-to input and output, and in my opinion anyway, there's no great reason for that. I think there are better letters we could be using. So I tend to pick T as our kind of default input, and that's because time is kind of one of the more common inputs we might use for functions. And then Q for the output, because some quantity that we're trying to measure. So T comma Q, here's our first component and second component. And so T is our input or first component of this function, and then Q is the output that goes along with T. So you might think of this as the X and the Y, which I won't fault you for, but I will try to steer away from those. And then this little asterisk here is trying to connect this rule with one special case. So the only thing that we have to be careful about with this rule for a function is that when you pick a particular input, it's only going to give you one output. And being a little bit cagey about how I phrase that, but so we start with some input and it goes to exactly one spot. So some notation, we could call a function f if we're feeling super lazy. We just don't want to pick another letter besides f for function, presumably. And this is entirely mathematicians' fault, but this is read as something like, it's not multiplication, this is f of some input. And so what we're saying basically is pick some input. This is the way that we write passing that into some function, and then the result of it, after it sort of cranks around for a minute inside that function machine, is whatever this output is. I realize this is still pretty abstract. We'll get to some examples here as quick as possible. To round out the last of our definitions, we've got all the inputs all put together, we call the domain. And all of the things in the output we call the image. You might have also seen this as the range if you've taken a class that's discussed functions before. Not a requirement, but just in case you have. And then the last thing is we say if you take an input that this function is not really ready to process, so something that's not in the domain, then we say that result is undefined. So maybe a very casual definition or example of this you might think of is if you ever try to put something metallic in the microwave, bad things happen. So if you think of the microwave as our function, putting metal into this microwave would cause it to malfunction. And so you might say in math terms that metal objects are not in the domain of the microwave function. I realize we're not mostly going to be dealing with microwaves, but that's one thing to think about. A function that may have a predictable output might be a toaster. So you take bread as the input, you put it inside the toaster machine, and out the other side, the outputs are toast. So in kind of our mathematical framing of this, sometimes we'll use these little kind of bubbly things where we think about here's where all of our inputs live. So this is the domain, so all of our inputs, and those could be numbers. That's typically what we're going to be operating with here. We have all the things we could get out the other side. So this is our image or our range, and inside of that are all these outputs. And then the thing that connects them, again, just trying to make a visual out of this, is our little function machine. So here in the middle, here's our function, and take some input, pass it through this little function, it thinks about it for a minute, and then it matches it up with whatever that output is. So to try to take this from the abstract and put it into a little more concrete terms, let's see if we can try an example that still doesn't involve a whole lot of numbers, so maybe save you from that. So pets of a particular family, spoiler alert, it's my family. We have JB and Blue Star, those are both of our cats, they're 2 years old. We have Zoe and Raindrop, who are parakeets. Zoe's 4, Raindrop's 5, and then we've got Cleo, our little doggo, who's just a year old. So we're going to consider a function. Again, we'll label it f just for, I don't know, laziness, why not? It takes its inputs, the name of the pet, and then the output will be the age of that pet. So we can start to see the rules sort of come together for this function. We're supposed to write all ordered pairs, and then we'll write those pairs in a table. So maybe we'll kind of do these things on separate sides. So ordered pairs are going to look like something, comma, something else. That's how they typically look. If you think about graphing from the past, this is like our x, comma, y. And if we look at our setup, we're supposed to take all of the inputs, those are going to be all in our first component here, and all the outputs will be in after the comma. So for instance, one combination of inputs and outputs for this function would be that JB, that's the name of the pet, we're supposed to pair it with the age, is 2 years old. So JB, comma 2 is one of the ordered pairs that defines this function. And then we can keep going. So Blue Star is the exact same age. They're actually litter mates. So we have another pair, Blue Star, comma 2. We have more pets. So Zoe is an input. That gets paired with the age of 4. Raindrop is 5. And Cleo is only 1. Just newly not a puppy. And I've kind of, let me make sure that looks like a comma there. So I've intentionally kind of written them in this vertical format because when we write this in a table instead, it turns out that we're going to see very much the same structure sort of come about here. So if we build ourselves a little table, it's going to have the same basic structure. And let's see if I can actually get myself a straight line here. We're going to have our inputs listed. We're going to have our outputs listed. So rather than try to get fancy, I'll write input, and then I'll write it both as output and using this function notation, this f of input. So when we look at our actual values here, we're basically going to be writing it in the same format as our ordered pairs, just with our input and then output listed on the other side. So it's really just a different organizational strategy for the same set of information. Basically, we're losing the parentheses and comma, and we're gaining a little table structure. So Raindrop pairs up with 5, and Cleo pairs up with 1. So there's both ordered pair and table. Let's think about domain and image. So domain is a list of all the inputs, and we'll try to go back to we won't put a lot of effort into it, but our set notation. So we have these little curly brackets that say, here's a big group of things. And the domain is a list of all the inputs. So we're not going to attach them to anything. All of our inputs in this function happen to be the names of pets. So I'm going to list all of these with little commas separating them. And put a little note on here I want my little squiggly brackets to say that these are a set of objects, a list of them. And just as to recall, this is a list of all of our inputs. That's what our domain is. And then for the image, the same situation, but now it's a list of all the outputs. So one little interesting nuance we're going to hit here, I'm going to write them in order of ascending numerical value, just so we can kind of see. So 1 is the smallest of our outputs, 2 is the next smallest, and I'm only going to write it once. We only really need to keep track of each output as a possible result. And so I'm only going to write those 4 numbers so that 2 only appears a single time there. You may have been thinking a minute ago, wait a second, Mike, you told me that functions are supposed to have an input go to one place. Isn't that a problem here where we have JB going to JB and Blue Star both having an output of 2? And it turns out this is where a little bit of that nuance kicks in. It doesn't actually matter that given one of these inputs, there's the potential for another input to go to this same number. Each input has a predictable output. That's the thing that we want. What would be a problem is if Blue Star had more than one age. You could imagine that being a slightly weird way to structure things, a cat being both 2 years and 5 years old at the same time. That seems strange, some kind of time paradox happening. But having 2 siblings be the same age, that's not so big of a deal, and that's kind of what functions are looking at, that predictable machine. So again, here is our image, which is a list of outputs. Making use of our notation, let's do f of raindrop. This is a very strange way to phrase this, but once we are working mostly with numbers, it doesn't feel quite so odd. But just as a reminder, this would be read f of raindrop. Again, a slightly strange phrasing, but there it is. So these parentheses are not multiplication. They're intending to ask us to take raindrop as the input and plug them into this function. So if we do that, f of raindrop, that means we're supposed to go to our f function, which is matching up pets with ages, and say, at an input of raindrop, what is the output? And since raindrop is 5 years old, we're going to write f of raindrop is 5. What about inputs for the function being undefined? So some place that we can pick as an input where this function doesn't know what to do with it. Well, you could try to guess whether there are other pets that I have in my house. There actually are. We have a whole zoo here, but this function only knows these 5 pets. So basically you could pick anything else, any number or a different name or a symbol or almost literally anything that's not on that list of 5, and this function would have no idea what to do with it. So for instance, we could pick my name. Mike is not an input that this function knows what to do with. So in other words, if we were to try to compute f of Mike, this is undefined. Because Mike is not on the list of things that are acceptable inputs. It's not in the domain. And then lastly, for this example, why did we not break this rule? So let's try to put into writing why that concern you may have had a few minutes ago is not actually an issue. And this is phrased in a much more mathematical way, but I think we can handle this. F of JB is equal to F of Blue Star. So if we were doing some translation here, maybe what we're trying to say is this is saying the outputs are equal. And that's not an issue because each of these 2 functions, each of these 2 inputs is handled by this function separately. So the upshot is f of JB is a single number. And so is f of Blue Star. And that's all a function needs, is that each time you pick an input, there's one predictable output. So the fact that both of these results are the same, they're both 2 years old, is not a problem for a function. So it's a little bit unfair because now you have this extra pressure on the inputs that's not present on the outputs. Each input has to go to only one place, but the outputs can come from all kinds of different places. Oh well, it still fits within the narrative of being a predictable machine though. Okay, last part. Add an ordered pair to the relationship so that f is no longer a function. All right, so we're supposed to take this setup, which you could think of either as a bunch of ordered pairs or as a table, and we're supposed to add something to it that breaks its function nature. So I'm going to scroll back so you can have a closer look at our table. And here is our list. This is everything that defines our function. Something that we could do that would break this, and maybe I'll pause. If you want to think about this on your own for a second, you can pause. What could we add to this table so that this would no longer be a function, such that now some input goes to more than one output? Because that's the only thing that makes this function, any function, break. So again, there are many possible answers, but I think the best approach would be to pick an input that is already here and then give it a different output than it had before. So we could let's pick the baby, let's pick Cleo. So if we added another ordered pair to this function that was Cleo, comma, anything other than 1, literally anything, Cleo, comma, 3, then now this is no longer a function. So let's specify again that there are many possible answers. So this would mean that Cleo, as an input, gets sent by this function to both 1 and to 3. And then in practical terms, we're saying Cleo, the dog, is both 1 year old and 3 years old, which doesn't make a whole lot of sense either. So the functions are really trying to grasp a predictable machine kind of relationship, which is great because it seems to make some sense in a lot of these applied contexts. We'll come back and we'll look at functions from additional perspectives.